quick synopsis of what we did while I was waiting for my two-factor authentication and couldn't get into Zoom, which makes me unhappy, but it should energize me. Okay. Vectors, we got dot product, we got cross product, we got projections. This is explained in another video and there'll be a link. Here's a picture of projections. Here's your scalar projection in terms of the cosine of this angle and the magnitude of V. Here's your vector projection, which is just a scalar projection multiplied by W over magnitude of W, the unit vector in the direction of W. Now, since V dot W is not just equal to V cosine theta, it's also equal to magnitude of V magnitude of W cosine theta. And you can prove that using high school trigonometry. It follows that this is just the magnitude of V cosine theta. I didn't write it with a magnitude. I wrote V without an arrow, meaning magnitude. But if we divide V dot W by magnitude of W, well, here we have it. V goes away, we get W goes away, magnitude of W goes away, we get magnitude of V cosine theta. So this matches this. In the vector projection, we just multiply by the unit vector in the direction of W. Okay, plane through X naught, Y naught. Well, that's not going to be path in space. You have a parameterized curve. You take its derivative. The derivative is a vector in the direction of motion. Unit tangent vector, you simply divide any vector in the direction of motion by its magnitude. In this case, we'll divide R prime by its magnitude. And I wrote that wrong. This is magnitude of R. It's magnitude R prime. Maybe a little hard to read. And that's the unit tangent vector. Now I said, yeah, okay. This is magnitude, this is T prime. T prime is normal to the curve, perpendicular to the curve. There's a picture down here. And this is because of isosceles triangles, and you should be able to prove that. The derivative of any vector, any unit vector, is going to be perpendicular to that unit vector. Okay, if you divide that T prime by its magnitude, you get a unit normal. R double prime's acceleration, you project R double prime onto T. Here's R double prime. The blue vector here is T. You project R double prime onto T. Vector projection is going to be a vector in the direction of the unit tangent vector. This is not going to have the same magnitude, or if it does, it's just coincidental. So here's your projection. This is your R double prime of T, your projection onto T of R double prime. That's not the normal component of R double prime. I don't think I ever really wrote it down. I said it. But if you subtract the unit tangent vector from your R double prime, you get the unit normal vector. So I guess I better indicate how we got that. Unit normal vector is and it's not the unit normal vector, it's a normal vector. I'm going to write that as R double prime minus R double prime parallel. That's succinct. And your unit normal could be calculated just by dividing R double prime perpendicular by its magnitude. Okay, now if you do know what your unit normal is, you could also get this vector, this purple vector, by projecting R double prime onto the unit normal. I haven't included that in the picture, but that's something that to make sure you understand. Then I mentioned the osculating circle. V equal m dot cross t is your binormal. The plane of motion is perpendicular to your binormal. In other words, the plane in which you are moving here is the plane containing the projection of your R double prime vector, which is your acceleration vector, if you wish, onto here. So it's acceleration in this direction. And here's the acceleration in the normal direction. And you get two vectors in the plane of motion and a binormal. So if you're moving along, you got your three vectors. Got your unit tangent, your tangent vector, your normal vector, and their cross product is the binormal vector. And I've got this backwards. It should be t cross m. Your osculating circle, I'll just say it, I don't have room to write it. I want to take the time. You're temporarily moving on a circle here. Okay, just between here and here, this is very close to the arc of the circle. Your osculating circle is the circle in this plane, the plane of t and n, whose radius matches this. The perpendicular component of your acceleration is your centripetal acceleration. Use the fact that centripetal acceleration is v squared over r, where r is the radius of your circle. You can calculate the radius of your circle. Okay. You have v, that's the magnitude of your parallel component, that's how fast you're moving. Okay. So you can easily enough calculate the radius of that circle and then move along this vector that distance, and there's the center of your osculating circle, and you can write the equation. Okay, that's pretty neat. It's a pretty neat idea. I'd like to say more about it, but time presses. Length through x naught, y naught, z naught, perpendicular to your normal vector. X, y, z is on the plane if and only if, that's IFF there, it's like IFT in the picture. If the vector from here to here is perpendicular to your normal vector. The vector from here to here is just x minus x naught I, y minus y naught j, z minus z naught k. So there's the equation. It's not a formula, remember. It's a picture. Okay. It's also a formula. If you know both the formula and the picture, then you pretty much understand it, and you can apply it better in novel situations. Line through x naught, y naught, z naught, parallel to v, just means that the vector from here to here, from x naught, y naught to x, same vector that we have here, is some multiple of v. Okay, vector is parallel to another if it's a multiple. So you just call that multiple TV. Okay, and you have it. Okay. Now we go to quadratic surfaces. Quadratic surface, you just take the square, a multiple of the square in the first power of each of your variables. So you've got an x squared and an x, a y squared and a y, a z squared and a z. And then you add a constant. And then you could complete the square on every one of these things. Okay. And this would be in the form of taking variables. want to spend too much time figuring out what my variables ought to be. Okay. Now I say if h equals k equals p equals 0, then this is true. There's another condition that it's not b, it's c, and it's not e. And A, C, D, all non-zero, then you have this sort of thing, okay? If A, C, and E are all greater than 0, this is an ellipsoid. Otherwise, it's a hyperboloid of one type or another. Now, I don't have time to categorize all these things, but you have to understand conic sections. Intersection with each quarter plane is either an ellipse or a hyperbola. If this is your origin, and this is one of your coordinate planes, well, the ellipse could be like so. You know, hyperbola. It'd be like so, or like so, one of these three. Now, I just recommend you look back at this picture where I drew it early in the semester and explained it rather thoroughly. Okay? I didn't explain it all that thoroughly, just here's how you construct it. And something about why and how you know which one it is. It's this, or it's this, which will consist of these two, or it's this, which consists of these two. And they're, you know, you got your A and your B, your major and your minor axes, semi-major, semi-minor axes, and so forth. So that's the general idea of a quadric surface. Now your text shows you all kinds of pictures and so forth, and ask you to classify them and match them up with their equations. I think they show you too many pictures. I think you got to develop your own pictures to really understand them. Because you see now how these surfaces help you visualize all the stuff that goes on in 3 dimensions, including multiple integrals and gradient fields and divergences and all that stuff. Okay. And many of the things you integrate over are quadratic surfaces. You've got a lot of paraboloids, spheres, ellipsoids, okay? So quadratic surfaces give you a good point of reference for understanding. You don't end up looking at a lot of hyperboloids because they're a little bit more complicated. Ellipsoids and paraboloids are fairly simple. Quadratic surfaces. We also have cases where one or more of A, C, and D are squared or zero, in which case you get paraboloids. You get elliptical or circular paraboloid. Or even simpler curves, okay? Don't want to try to name them because I can't think of the name right now. Don't want to try to draw them because time doesn't permit. Okay. Now, I'm trying to do a quick synopsis of the whole course. It ain't going to work. You can't do the quick synopsis of the whole course in an hour and a half, okay? At this level of detail, because I'm still in basically the first chapter, haven't addressed a whole lot of other stuff. So I'm going to get a little sketchier with it. And when you have curves like this, you have arc lengths, okay, and curvatures. Well, first you got to understand this before you can understand arc length and curvature. So I'm going to have to delay talking about arc length and curvature. We kind of need to move on right now. But it's within this, okay? Your arc length, you partition, you know, the P word that kept coming into my head was parameterize. You partition your T interval. And then for every T interval, you multiply the length of that interval by how fast you're moving, which tells you how far you move. Take your limit, you get your interval. I can do that next time, I hope. Or maybe I'll do a supplement. Can't do it till Thursday afternoon, but maybe I'll do a supplementary video. Depending on whether things actually work. I think I commented to somebody else, if I get my hands around the throat of technology, we very quickly not have any more technology. But we need the technology and it's great, except when it doesn't work and delays everything. Okay, so we have this. The whole idea of parameterization, which you're running into at this point, you know, you got to parameterize surfaces before you can do Stokes' theorem and divergence theorem and all that stuff. Okay, because you have surface integrals involved with both. And that's an extension of parameterization. We're not going to talk in detail about that today. But you understand how early in the semester I said you really got to understand parameterization. Parametric curves, which you're supposed to have covered in prerequisite courses. Due to COVID, maybe other circumstances, those things didn't get covered very well, obviously. Okay. And I told you at that time, you're going to have to go back and work through that chapter, okay? To really understand it well enough, close out the course. Now we have to understand parameterization well enough that we can apply it to surfaces in 2 dimensions, okay? And I don't know that we're there yet, okay? Although, you know, next time, after you've had time to review the chapter on vector calculus, Stokes' theorem, Green's theorem, you know, surface integrals, all that stuff, divergence, curl. Then I can come back and talk about that, okay? it'll make more sense. And your assignment for Thursday is going to be the review of that whole chapter. Okay. So we'll come back to that. Unless there's something else that you need me to do. Okay. So fairly simple idea now is functions of several variables. But what do we do with them? Okay. So I'm going to assume you understand functions of several variables. I think people have no real problem with that. I'll call that functions of more than one variable. We can understand a lot about functions of more than one variable by just understanding a function of two variables. And adding variables just adds a little bit more calculation. And it's important to also understand functions of three variables and visualize them in space. Okay. And of course, really understanding quadratic surfaces, contour plots, all that kind of stuff is valuable for being able to visualize stuff in space. Okay, well, functions more than one variable. Okay. An example, not a specific example, but function of two variables. Has a three-dimensional graph, as you know. And I don't have to detail that. I'm looking at my notes here. I mean, I've just got a list of topics. Just only I can read my handwriting, and sometimes I can't even do that. Okay, so anyhow, you got a function three-dimensional graphs, and that's just looking to see if I'm forgetting something, but I'm going to go on with partial derivatives. Okay. So if you have a three-dimensional graph up here someplace, and I don't want to draw the whole three-dimensional graph. I just want to represent the graph in the neighborhood of a point in the x, y plane. So here's a point. And up here is the point. Again, I think what we're to label it. Point x, y, f of x, y. Now, if you slice the surface, by holding y constant, well, if y is constant, then you have a plane perpendicular to, perpendicular to the y direction, perpendicular to j vector, but parallel to the x and z plane where y is constant. And within that plane, you have a curve and the partial of f with respect to x equals I like to say just the derivative of f with respect to x. Within the plane where y equals constant. And then that, of course, indicates the slope of this curve at this point. And that would be the slope of the so-called blue curve at this point. Now, we've drawn that figure several times. Hopefully you've pondered it a number of times, so you have a pretty good understanding. That, for example, then allows us to get a vector here, parallel to that slope. Okay. So this vector I plus partial f with respect to xk, where this partial derivative is calculated at this point, going to be tangent to the three-dimensional graph. So we have this, excuse me, tangent vector. So this picture corresponds to this tangent vector. Or this picture corresponds to this tangent vector. Similarly, you could hold x constant, and you get a curve where z is a function of just y. Of course, this is why you hold x constant or hold y constant when you do the partial derivative, which you know to do to make sure you understand why you're doing it. Okay, so let's just say that this curve does this sort of thing. And similarly, just totally analogously, you get I can't even write down that low. I'll say just also because I don't want to try to write out the word analogously. Okay. J plus partial f with respect to y times k is also tangent to the curve. And that vector will indicate here. Well, you take the cross product of these two vectors, you get the normal. So now you can approximate the surface near this point by its tangent plane. Near x, y, f of x, y. You got the tangent plane normal. To the vector that's the cross product of these two. So you calculate that cross product. This gives you k. This gives you negative fy. No, this gives you, sorry, fy j. And this times this gives you, let's see, k cross j, negative, wait, something's wrong. I cross k is negative j, yeah. So you get negative fx j and negative fy k. So you can write that out very easily. That's going to be your normal vector. You got your point, so you get your plane just using this idea and the picture of a plane perpendicular to a point, a plane through a point perpendicular to a given vector. Okay. You should ponder why this is a differential approximation. Of f of your function of two variables. Okay. Or a linear approximation, if you like. Now we've got the chain rule, which you apparently know how to use, and so I'm not going to go over them at this point. The directional derivative the same picture if you move in some direction not parallel to the x or y direction. I'd like to go over the details, draw another picture, but we're short on time. Directional derivative in the direction of u is fx cosine theta plus fy sine theta. You should understand this makes a lot of intuitive sense. If you're moving in this direction, then this vector makes angle theta with the x-axis. So any change along the tangent plane is going to have, it's hard to state without a picture, but it's going to have a component essentially that's proportional to how close this vector is to the x-plane, which is your fx cosine theta, and how close or far away it is from the y direction. I said x-plane. This vector is close to the x direction. If you move it in the direction of a u vector here down in the plane, this vector is closer to the x-axis than it is to the y-axis. Okay, theta, of course, is a direction. It is always the angle with respect to the direction of the positive x-axis, counterclockwise angle. So it makes sense that your directional derivative in this direction, which is just the rate at which the function changes as you move in this direction, is going to be closer to fx than it is to fy. And of course, if you're in this direction, theta is a small angle, and the cosine is going to be bigger than the sine. If, on the other hand, you're out in this direction, then you're going to have a greater contribution from the sine. Now that could be made rigorous. We did it. Your book also does it. And theta is the angle of u with a positive x direction. The gradient of f a little hard to read that word. It's in the direction is that of the maximum increase. The magnitude is the rate of maximum increase. And the directional derivative is that gradient dot with u, where u is a unit vector. Assuming that the magnitude of u is 1. Because a unit vector can be written, unit vector in the xy plane can be written as cosine theta times I plus sine theta times j. Of course, it's important to understand why that's the case. That's another thing you want to try to make sure you understand. Okay, we're running very short on time. We could still talk about maxima, minima, and Lagrange multipliers. We're both out of time and out of board space, so we're going to have to put that off. Maybe I do that in another video. Maybe we spend time in our last class doing that, but maybe we spend time in our last class reviewing chapter 15, which is the crux of the whole course. Okay. And if we don't get to do all that, which is likely, I'll do a video